What's a general strategy you can use to approach solving trigonometric equations? Well, first of all, what are we referring to when we say use the term trigonometric equation? And you might say, well, it's an equation that has a trig function in it. And that's not technically correct, because you can think about the trig identities. These are all equations that have trig functions in them. But this is not what's being referred to as a trigonometric equation. Because, so if you think about equations from algebra, there were three. When you solved an equation in algebra, there were three scenarios that could take place. The equation could be an identity. The equation could be a contradiction, or it could be conditional. The identity was when you solved the equation, you did all the subtracting, adding from both sides, multiplying both sides, and you got down to the point where you got like 5 is equal to 5, or you could subtract 5 from both sides and get 0 is equal to 0. What this meant was that any input, as long as it was in the domain of everything in the equation, any input solved the equation. And if you think about it, that's what the trig identities are. They're valid for any input theta, as long as it's like you can input any value of theta as long as it's within the like tangent. You can't input certain values in the tangent. As long as it's within the domain of everything in the identity, it's valid, right? That's why they're called trig identities. A contradiction was the case where you simplified and you got something like 0 is equal to 5, which is not true, and that meant that there were no solutions to the equation. And the conditional case is what we were most familiar with. That's when you got something like x is equal to 1. There was one solution, or maybe like with a quadratic equation, you got x is equal to 3 and minus 2. And the technical way you think about conditional is not that you get finite number of solutions. It's that the equation is satisfied for certain values within the domain and not satisfied for other values. And I point that out because with trig equations, this is what we're talking about with trig. When we say trig equations, we're talking about equations with trig functions in them that are conditional. But with trig equations, it's not going to be a finite number of answers. It's actually still going to be infinite because the trig functions are periodic, but they're still going to be unique in the sense that there's going to be some values within the domain that aren't going to satisfy the equation, but then some that will. So it's the conditional case. It's kind of like the equations we solve in algebra and get actual answers to. We're thinking about those in terms of, okay, what if they have trig functions in them? Okay, now when you're presented with a trigonometric equation, there's two scenarios, general categories you could put the trig equation in. Okay, first, do all of the trig functions in the equation, are they all single angle, or do some have multiplying factors or something going on inside of the trig function? So what I mean by that is, if all of the trig functions they could just have, like the sine of x minus cosine of x is equal to 3. This is a trig equation that it's just sine of x, cosine of x. There's no cosine of 3x or cotangent of x divided by 2. So if all of the trig functions have just they're just single multipliers, then that's one category. But if you have trig functions that have stuff going on inside of the arguments, at least one of those, then it falls into this other category, non-single angle, you could say, categories. Like this is a triple angle, this is a half angle, these are single angles. So you could have like a trig equation, maybe you could say it's a single, it contains all single angle trig functions. Or even, a shifted trig function, maybe sine of x plus 2. Then if you had one of these in the trig equation, that would fall out of the category of strictly single angle. So we want to start by thinking about how do we approach single angle trig equations. That'll be a good foundation. Once we understand how we would approach solving these, then we can expand that out to think about the more complicated case where you have trig functions like this. Okay, so, all right. The general way you want to look at, okay, we're dealing with trig equations that have just single angle trig functions. The general approach is going to be that you would like to get the exact same type of single angle trig function throughout the entire equation. That's what you would like to do. if you could somehow do that. So maybe here we could, we'll come back to this later, how we would look at this later, but you want to get it to where, if you can, to where you have just one type of trig function, single angle trig function in the equation. Okay, now why is that? Why is that desirable? Well, because, okay, when we have something like this, right, they call this a linear trig equation. Why do they call it that? Because we can say that we can substitute a variable for sine x. But you can imagine we could do this no matter how complicated the trig equation is, even if it's got all kind of, multiple signs of x's all over the place, we can still do this and turn it into an algebraic equation. And in this case, if we make the substitution, it turns it into a linear algebraic equation. That's why they call this linear. But if we had, we would do, so we've got u plus 2 is equal to 3, subtract 2 from both sides, u is equal to 1. Okay, we've solved the linear algebraic equation, but now u is equal to sine of x. Okay, but now we know how to solve this. This is just inverse trig functions. And there you go. Now, just you have to understand how the inverse trig functions work, and you would we'll come back to this. Okay, let's just say we stopped at this step. We'll come back to this because we're not really done yet. But what I'm saying is, so like here again, if we have it all in terms of just one type of trig function and a single angle. And you can imagine this would be fine if they don't have to be single angle. Even if these were like both triple angle, as long as they're both the same, that's going to be advantageous. But right now we're focusing on, it's only a problem if you have it like mixed in, like this is secant 3x and this is secant x, then you have more work to do. But just focusing on single angle now, if we have all the same single angle type of trig function, then we just say, okay, u is equal to secant x, and we're going to transform it into a algebraic equation. In this case, it's going to be linear again. So subtract u from both sides, subtract 1 from both sides, so secant x okay, so x, and then you're done. You're done with at least there's more to interpret, but like you've solved the equation. This is just a matter of, we just need to talk about what you do from here. But you're done. And so, okay, here's another example. This was another linear trig equation. Okay, this one's not linear, but again, we've got just one type of trig function. Okay, so we just say we can say u is equal to secant x and transform it into an algebraic equation. In this case, it's going to be quadratic. And just go ahead and solve it. So subtract 2 from both sides. And actually, there's no solution to this because there's no number. When you square, you get a negative number. But you can imagine maybe there would be a solution, and you would, I mean, yeah, let me actually, I'd rather give you an example that has a solution here. So let's say this was 4. Okay, so u is equal to secant x, so u squared plus 2 is equal to 4. Subtract 2 from both sides. Okay, take the square root of both sides. Okay, so what we've got is the answer. So we've got u is secant x, so secant x is root 2, or secant x is minus root 2. Either one of these scenarios solve the equation. So okay, it would be if x is equal to inverse secant root 2, or x is equal to, right, either one of those. You see? Here we've got one type of trig function, so we can just turn it into an algebraic equation. U is equal to cosine x, so 2u squared minus root 3u is equal to 0. Well, we know how to solve this. We factor out a u, so 2u minus root 3. So u is equal to 0, or 2u minus root 3 is equal to 0, so u, okay, so cosine x is equal to 0, or cosine x is equal to root 3 over 2, so x, okay, x, just like that. All right, so that's the general idea. If you have one type of trig function, then you can just turn it into an algebraic equation and solve it. That's the first way you want to approach looking at a trig equation. Okay, specifically right now we're thinking about if you just have single angle trig functions. Okay, so but now once you get to this step here, once you get to this step, where do you go from here? Well, you need to, okay, to solve trig equations, you need to make sure you understand the inverse trig functions very well. So go through the opening section of chapter 6, everything we talked about, the example problems. You need to be really familiar with how inverse trig functions work. Okay, because the way you're going to need to look at this is, so we know the inverse trig functions are, they are functions. The original trig functions domains and ranges are restricted to allow us to create a actual function from the inverse. So the actual answer to a inverse trig, you know, like inverse sine, cosine, whatever of something, is really technically only one answer. However, we talked about, though, that every time you do evaluate an inverse trig function, it's good practice to where you're always going to go ahead and think about, well, in general, what does the question that the inverse trig function is asking, what are all the answers to this question? Because a lot of times it's going to be the case that you're going to need to consider those other answers based on the problem you're working on. And this is one of those cases to where, since the original question is this equation, yeah, technically there's only one answer to this, but in reality, there's going to be, what the question that this is asking is, what angle, when you take its sine, do you get 1? Okay, there's an infinite number of answers to that question. And in actuality, all of those answers will solve this equation. So yes, even though if we, okay, so what's the inverse sine of 1? Sine is equal to 1 only at one angle, the 90-degree angle. Okay, and you could do this with degrees, radians, it doesn't matter. We'll do it in degrees just so it's clear. There's actually only one angle when you take its sine. Do you get 1? At least one. There's only one angle between 0 and 360 where that's the case. Okay, and so the domain of, or the range of inverse sine is minus 90 to 90. So there's only technically one answer to inverse sine of 1, and that's 90 degrees, technically, based on inverse sine. But we're going outside of that. The common practice when you do an inverse trig evaluation, you want to think about, well, what angles also answer that question, though? What angles also answer this question of what angle, when you take its sine, do you get 1? And we know it's going to be 90, and actually any angle that's coterminal with 90. So that would be 90 plus 2 pi times n, where n is any integer. Or no, it would be 360. So technically, this is the true answer to the problem. And if you were doing a real-life problem, if this was actually something you were modeling in real life, you'd have to just analyze your problem to see, okay, which angles am I actually interested in? Again, if this was for something you were modeling in real life, the way you would approach this is you'd get the general answer, and then you would look at the specifics of your problem to see, okay, which there's a certain angle that's pertinent to this problem, and you'd pick out that angle. That's how you would do it. Okay, but now, when you think about inverse trig functions, I want to point this out. I don't think I made this very clear when going through the inverse trig function chapter. I think I stated it wrong. But in general, if you have an inverse trig function that's corresponding to some angle that's not a quadrantal angle, In this case, this was corresponding to a quadrantal angle. If it's not corresponding to a quadrantal angle, then there's always going to be two angles between 0 and 360 that satisfy the question asked by the inverse trig function. Not the inverse trig function itself. There's only one answer to an inverse trig function because it's a function. But when you take a step back and look at the big picture and say, okay, what angles answer the question that the inverse trig function is asking, and that what angle, when I take its sign, gives me this value, then there's infinite number of answers, right? And for the case where, again, where you're dealing with a non-quadrantal angle, there's going to be two angles between 0 and 360 that satisfy that question. And so then, but then when you take the full general from there, it would be those two angles in any angle that's coterminal with those two angles. Now, what I was stating in the previous video, or in the inverse trig function section, was that if you have a quadrantal angle, then there's actually only going to be one angle between 0 and 360 that satisfies that question. And that's actually incorrect, because in this case it's true. But if you do have the case where if you were dealing with inverse sine of 0, for example, okay, the answer to this as a inverse trig function is just 0 degrees, right? Because the sine of 0 degrees is 0. However, it actually is this is a case of a quadrantal angle where there's another angle between 0 and 360 that satisfies this question, and that's 180 degrees, right? Because sine 180 is 0. So 0, 180, I mean, this is not the answer to the inverse trig function, but you get the idea. This is not technically correct to say inverse trig of 0 is equal to 0 and 180, but thinking in general, we can put this. So, but as far as the question, what angles, when you take their sign, do you get 0? That would be 0 degrees, 180 degrees, and any angle coterminal with those angles. But with the other quadrantal angles that correspond to a non-zero value, it's only going to be 1. That's the way it works. If you're taking the inverse of a number that's not 0, and that corresponds to a quadrantal angle, there's going to be one angle between 0 and 360 that satisfies that answers that question. And then in general, it'll be any angle coterminal with those. I just wanted to point that out. It's not a big deal. I just wanted to make that correction. I think I'd stated in the inverse trig function section, I stated that all quadrantal angles with inverse trig functions are going to have one value between 0 and 360 that answers the question, that the inverse question, but that's actually not exactly true. Okay, so now here, x is equal to inverse secant of 2, so we can come to the 30, 60, 90 triangle. 1 root 3, 2. And so secant is hypotenuse over adjacent, so that would be secant of 60 is 2. Okay, and so what we want to think about is that the technical answer to inverse secant of 2 is just, so secant, the range of secant is, it's minus 90 to 90. So we would just give 60 degrees. That would be the because it's positive 2, we give 60 degrees. Okay, but as we know, that's the only answer to inverse secant of 2. But again, every time you do an inverse trig function, no matter what it is, no matter what the scenario, you always take a step back and ask yourself, okay, but what other angles, when you take their secant, do you get 2? Outside of just 60 degrees. Well, okay, secant's positive in quadrants 1 and 4. Okay, yeah, so actually, no, the range of secant is, it's 0 to 180, actually. But still, it's still 60 degrees because it's positive. Okay, but, so secant is positive in quadrants 1 and 4. So there's another angle in quadrant 4 that has reference angle 60 degrees that would satisfy this question. So 60 degree reference angle quadrant 4 is what? 300 degrees. Okay, so what you say then is that in general, any angle, if an angle of 60 degrees, 300 degrees, or any angle coterminal with these two angles would satisfy this equation. And then you just ask yourself, okay, what is this equation modeling? What's the purpose of this equation? And from that, you'll see which values are pertinent to your problem of all of those potential values. Okay, same idea here. You would just get, so these are not quadrantal angles corresponding to quadrantal angles, so you're going to get 2 angles between 0 and 360 here, 2 more angles here. So that would be, you'd have those 4 angles. Any angle coterminal with those 4 angles would all satisfy this equation. Okay, so now what are some other scenarios where we're still dealing with these single angle trig equations? Well, okay, if we come back to this example, you could have a case where you've got different trig functions mixed into the same equation. So now we can't just make a simple, say, u is equal to sine x and turn it into an algebraic equation. So what do we do here with these types of scenarios? Well, what we're trying to do is we want to see if we can manipulate the equation to get it to a point where we can make that substitution. So we could add something to both sides, square both sides, use trig identities, any kind of equation manipulation combined with trig identities we could try and use to manipulate the equation. So what we can think about is that we know that there's a trig identity that, well, you can always think about the reciprocal identities. That's one thing to always think about. So if we had, like, if this was sine x minus cosecant x is equal to 3, well, cosecant is the reciprocal of sine, so now we multiply this entire equation by sine x, and you've got sine squared x minus 1 is equal to 3 sine x, and there we go. Now we say u is equal to sine x, and we're left with u squared minus 1 is equal to 3u, and we solve it from there. Okay, so yeah, I guess you want to start with, when you've got a mixture of trig functions, start with, can you use a simple reciprocal identity to get it in terms of one function? That would be the place to start. Look at the reciprocal identities. But if it's not that simple, then you look at the other trig identities. So we know that sine squared plus cosine squared is equal to 1. So we can add cosine x to both sides and then square both sides of the equation. Now, what's important to remember with trig equations is that you always want to constantly be thinking about the corresponding parallels to regular algebraic equations. That's important. You always want to have that in your mind. And what I mean by that in this case is that, remember, with an algebraic equation, the times where we squared both sides, we didn't do this often, but it was mostly in the case of if you had a radical equation, because you square both sides to get rid of the radical. But when you do that, though, you have to be aware of extraneous solutions, because the process of squaring can introduce extraneous solutions. And that's going to be the same case here. You have to be aware of that potential. Now we do. And in the case, if we had an absolute value equation that had trig functions in it, we apply those same parallel principles to algebraic, to absolute value equations that we found in algebra. We solved in algebra. Those can have extraneous solutions based on. It's not like if you do anything wrong, you get the answer doesn't apply. You could not make any mistakes, and you still get an answer that doesn't satisfy the original equation. So squaring both sides is one of those cases where we have to look out for this. So, okay, we get, why do we want to square both sides? Well, let's see. So we've got 9 plus 6 cosine x plus cosine squared of x. Okay, that's what this simplifies to. Okay, but now we can say that sine squared is 1 minus cosine squared. And now look what we have. We have all cosine x's. So let's simplify a little bit more. Well, actually, the cosine squareds actually subtract out, which is nice. But that doesn't. If that didn't happen, it wouldn't be a problem, right? Because we would end up with a quadratic equation. But it's nice that it did. Okay, I'll take it. So let's see. 6 cosine x plus 9 is equal to 1. Subtract 9 from both sides Divide both sides by 6. So you have cosine x is equal to minus 4/3, and that's actually not a solution anyway, because cosine is going to be between minus 1 and 1. This is greater than, or this is, the magnitude of this is greater than 1, so I guess this is not the best example. Let me, I want to show you that there's no solution here, is what this is telling us. But if I adjust this to where we get, let's see, if this was a 1, what would happen? So you would get 1 and then 2. Okay. So you get 2 cosine x is equal to 0. I guess we can work with that. So, okay. I'm trying to illustrate the extraneous solution potential that you have to look out for. So 2 cosine x is equal to 0. So cosine x is equal to 0. So x is equal to inverse cosine of 0. All right. What angles, when you take their cosine, do you get? 0. That's 90, and it's also 270. Okay, so 90, 270, and any angle coterminal with these, but this is a case where you need to check your answers. So, okay, but we can look at it this way. We don't have to, you say, well, how do you check an infinite number of answers? Well, no, we look at it this way. So the positive vertical angle, positive vertical, that's what 90 is. If you have sine of that, what do you get? You get 1. If you have cosine of that, what do you get? You get 0. But wait a minute, I got to change this. I changed this to, okay. Yeah, I changed the whole equation. Okay, 1 minus 0 is 1. So you look at all positive vertical angles are part of the solution. Positive vertical angles. Okay, what about 270? So sine of 270, that's negative 1. Okay, now cosine of that is 0. Negative 1 minus 0. Negative 1 is not equal to 1. So the negative verticals don't count. So these are the only answers. Okay. Okay. Here's another one where you've got mixed trig functions. And so you might say, okay, well, just divide both sides by cosine theta. But again, you want to think about the parallels to algebraic equations. When it comes to an algebraic equation, if you had something like 8x is equal to x to the 4th, and you needed to solve this, we know from algebra you don't do this. And then take the cube root of both sides. X is equal to 2. You don't do it that way because you're gonna lose a solution. Because you divide both sides by x, but that x can't be 0 when you do that. So the way you actually do this is it's a polynomial equation. You bring everything to one side. You get x to the 4th minus 8x is equal to 0. Then you factor. Then you use the zero product property. X is equal to 0. So this is x is equal to 2. X is equal to 0. So now now we have both solutions. Dividing both sides by x, we only got one of the solutions. So in that case, what we want to do is subtract cosine x from both sides. Cosine theta. Factor out a cosine theta, and you get sine squared theta minus 1. And now use the zero product property. So we've got cosine theta is equal to 0, or sine squared theta is equal to 1. So theta, okay, now here we've got sine theta is plus or minus 1. So sine theta is equal to 1, or sine theta is equal to minus 1. So theta, or theta, like that. Okay, now, so how do we deal with equations that don't have the trig functions with just the single angles in them, like double angles, triple angles, etc.? Well, okay, there's two ways to approach this. One way is that I guess a general way of looking at it is that if you can use trig identities to convert the double angles and the triple angles into single angles, all single angles, then you can solve it with all the methods we just talked about for single angle trig equations. So if you have any kind of single angle or double angle trig function that has a multiplier in it, you can use the double angle formulas, the sum to difference formulas, half angle formulas, because you might have sine of 3x. Well, there's no triple angle formula or sine of 5x or whatever, but you can write sine of 5x as sine of 3x plus 2x expanded out using the sum to difference, and then sine of 3x you could write as sine of 2x plus x. So you could get it into double angle or single angle, then use the double angle formulas. So there's ways of converting all of the trig functions in an equation to all single angle trig functions. And then you're left with, just use the strategies that we just talked about for single angle trig equations. But there also is the option, you don't have to do that every time. There also is the option of, so you can think about, if you have an equation that, if you can get the equation to where it contains all the same trig function, no matter what it is, single angle or not, then you can use the methods that we just talked about. So what I mean is, like here, okay? Do we need to write this as tangent? So tangent 3x is tangent 2x plus x, and then use the sum difference identity for tangent and then go from there? No, absolutely not. Because we've already got, this is linear in tangent 3x. We just say that u is equal to tangent 3x. So we have 3u is equal to root 3. We don't have that. This is redundant. I mean, obviously, you just divide both sides by 3, but this is technically a linear equation with tangent 3x. So you've got tangent 3x is equal to root 3 over 3. Okay, and then you just take the inverse tangent, and you get 3x is equal to inverse tangent. Okay, and so okay, now you're done. So we didn't need to convert this to single angle tangents. You can see, but this could be extended to any scenario. You could have a bunch of tangent 3x's everywhere, and you make the substitution, you get some quadratic equation, and you solve it, and you solve it the same way that we just did. So if you can get an equation to have all of the same type of trig function, regardless of if it's a single angle trig function, you can solve it and with all the methods we just talked about. Okay, now there is a caveat though, in that when you solve it this way, if you look, this is a little bit different than what we were just looking at with the single angle situation. And the way you look at this is, so we're gonna say inverse tangent root 3 over 3. So that's not a special angle where we can just use the reference triangles. So oh yeah, it is 30, 60, 90. That's 1 over root 3. So tangent of 30 is root 3 over 3. So what we've got here, we just do it this way. We say, okay, this is 30 degrees, but then also tangent's positive in quadrant 3. So what angle in quadrant 3 has reference angle 30? That's 210. Okay, so the x's that solve this equation are 30 degrees, 210 degrees, and any angle coterminal with those divided by 3. You see, so it's any of those other angles, divide either any of those angles by 3. That's an x value that satisfies this. And you could think about if you had an equation with like tangent of x plus 15, and then you is equal to something, and you took the inverse of both sides, it would work out the same way. You would have the inverse tangent value in all those angles, and then you take any one of those angles and you apply the extra operations, like plus or minus 15 in this case. You'd have x is equal to, let's say this is y. You have x is equal to inverse tangent of y minus 15. So you'd have any of those angles, subtract 15 from it would be an x. Okay, now what do we do here? And in this scenario, now we need to think about, let's convert this to all single angle. And then we'll have a regular trig equation with all single angle that we learned how to solve at the beginning of the video. So sine of 2x is 2 sine x cosine x. Okay, so now what do we do? Well, we're not going to divide both sides by sine x. We're going to, okay, now we factor out sine x. Okay, so we've got sine of x is equal to 0, and then 2 cosine x is equal to 1. So cosine x is equal to 1/2 x like that. See? Now, it also might be the case where we need to go the opposite direction. So here, we can notice that if we did, so we could write this as 1/2 times 2 sine x cosine x is equal to 1/4. 2 sine x cosine x is sine of 2x. Divide both sides by 1/2. That's going to be, so you've got like that. And then you just evaluate the inverse trig function and list out all those angles. What about something like this? Do we need to convert these to single angle? Maybe, but we want to first see if we can just solve these with just leaving the single angle as is. If we can get it in terms of all cosine or all secant, well, we know secant is a reciprocal of cosine. So no, we don't need to convert it to single angle, because now we can say, okay, u is cosine theta divided by 2, so 1 over u is equal to u, so u squared is equal to 1. Okay, so we've got cosine of theta divided by 2 is equal to 1, or cosine of theta divided by 2 is equal to minus 1 satisfies this. So okay, so theta like that. So that's the general idea of how you approach solving trigonometric equations.